presenter, who's Adrian Harris. You're unmuted now, Adrian, and we'll just change over to you. You are in control now.
Okay, thank you, Alison. Good morning, everybody. I guess good morning for most people and good afternoon for others. My name is Adrian. Following on from Mike's presentation, I would like to take you through some case examples of high temperature nanoindentation and some other associated techniques. So, the presentation is loosely based in the order of increasing temperature. So to start with, I'd like to start with a polymer example, which is a lower temperature application, as you would imagine. Then going up through the temperature range, approximately in order, to look at some solder samples. Then I'd say bulk samples, just a couple of examples that cover the range about 500, 600 Celsius. Then going up to some 700 plus Celsius applications in the form of materials for ceramic or solid oxide fuel cells, also some cutting tool coating materials, and then also some perhaps we would regard as more recent developments in the last few years. People have started to do micropillar compression work and microcantilever testing. Again, this is still done with a nano-indenter instrument. I was going to talk a little bit about controlled environments, but Mike's actually introduced that fairly well for us. But I will point out at various points in this talk where the controls environments have been used. So the bottom left of this screen here, a rather nice image, which is actually courtesy of Maurice Figueiredo. I think he's on the audience list at the moment, of an indenter glowing quite nicely there at 750 Celsius. So, example number one is a PET film, so a polymer film material, which you have three different samples which are chemically the same, but in terms of their microstructure they're rather different, and their microstructures have been modified by mechanical working. So we have an undrawn amorphous PET film, so you can imagine the chains are all kind of randomly tangled up. Then we have a uniaxially drawn equivalent material, so the material's been stretched in one direction, so we've imparted some order into the microstructure there, and then a biaxially drawn material of the same chemistry. So even more order has been put into the material through biaxial mechanical working, basically stretching the material. So what we can see using the nano-indenter is that if we run indentation measurements at a range of temperatures from 60 up to 110 degrees Celsius, we can see that, as we would expect, the hardness of the material drops, but interestingly, the biaxially drawn PET film does not drop in hardness anywhere near at the same rate as the other two materials. So, as we continue to increase the temperature range beyond, say, 90 degrees Celsius, we actually see that the undrawn material actually starts to go through a crystallization process and actually starts to get harder. And that response is actually shown as well in the modulus data from the same, the modulus results rather, from the same indentation data. So moving up the temperature range, this is an example on a lead-free solder material. As a lot of you are probably aware, lead-free solder is quite a current development topic. Lead-frees are replacing lead solders for a number of reasons at the moment. There are some problems that come from that, relating mainly to reliability of solder joints, particularly when you start to look at critical things like medical devices and aerospace applications. So it's important to be able to optimize these materials for optimum reliability, and to be able to do that we need to be able to characterize these materials mechanically. So here we have some work that was carried out by one of our customers in Singapore, where they carried out indentation measurements from room temperature up to 200 degrees Celsius. What they're particularly interested in is the creep, so the time-dependent behavior of these materials as they go up through this temperature range. So it's quite useful and quite easy, or fairly straightforward, to extract things like creep activation energy from these data here on the right, which are basically these sections of data. So we've loaded up here, finished loading, then held for a period of time, during that period of time the indenter continues to travel into the sample surface. So the better your stability of your instrument, the longer you can hold the indenter on the surface and look at these properties. So moving up the temperature range, so between 500 and 650 degrees Celsius here, this is just a piece of silicon wafer. So we have two sets of indentations here. We have, as I say, one set at 500 Celsius, another set at 650 degrees Celsius. So just to point out a few features or a few interesting points here, between 500 Celsius and 650 degrees Celsius is quite a critical temperature for silicon. It undergoes a lot of softening during that temperature range. Some other things we can notice from the indentation data here are, if we think about that creep data we saw on the previous slide, we can see that during the maximum load dwell period at 500 degrees Celsius, we get a moderate amount of creep. We go up to 650 degrees Celsius, that amount of creep is basically doubled or more. So another thing that we can actually see from these data are at 90% of the way down the unloading slope, we stop unloading and we can hold for a period of time, typically 60 seconds. We often use these data for correcting our measurement for thermal drift purposes. But what we can also look at here is viscoelastic recovery of the material. So we can actually see that there's a small change, maybe a slightly more viscoelastic recovery of this material at 650 degrees Celsius than there is at 500. So there we're looking at time-dependent properties. So continuing with the silicon, here's an interesting little set. So we have about 20 indentations here going from 5 millinewtons going up to 200 millinewtons. All of these indentations were carried out using the same loading time. So it took 30 seconds to load to 5 millinewtons here. It took 30 seconds to load to 200 here. So what that means is each of these indentations has been loaded at an incrementally higher loading rate. So that means that we've got less time available really for the material to undergo this viscoplastic, predominantly viscoplastic deformation, as well as the instantaneous elastic deformation that takes place. So what happens if we repeat this set of experiments, but we use a constant loading rate? What happens then is all of our loading curves superimpose. Okay, so this is quite important. This is quite a nice little demonstration of how, with sufficient stability, you can start to quite accurately quantify the time-dependent elements of a material's behavior. So this is moving up a little higher in the temperature range. So here we're going up to 725 Celsius. So we have two sets of data here, one labeled Quinto. So the Quinto data is actually some historical hot hardness indentation data. So that's a more traditional technique which a lot of you are probably familiar with. The indenter is driven into the surface, the residual imprint size is measured, and then the hardness is typically read off of the Vickers hardness table. That's fine for bulk samples, but not so good for thin film materials. But we actually just repeated some of these measurements using a nano-indenter recently up to 725 degrees Celsius. And got quite a nice correlation. It's just a nice demonstration of how the technique can be compared with other more traditional techniques. Incidentally, these measurements were carried out in an argon atmosphere, as the cobalt binder in the tungsten carbide materials oxidizes very readily, causes the material to expand, and basically very much limits your maximum measurement temperature capability and also the amount of time you have available before the sample degrades too far. So thinking about what goes on top of those cutting tools, mostly the coatings. Coatings designers have quite a difficult job to manage. They want to optimize their coatings for predominantly high hardness in high-speed cutting operations. So during these high-speed operations, frictional interaction between the tool and the workpiece causes a lot of heating. That softens the material. It also changes the ratio of the elastic behavior of the material to the plastic behavior of the material, so it's plasticity index as we refer to it. And also the impact resistance of the material. It's very important to know about that, particularly when you're looking at milling operations where the cutting is interrupted. So some of these things we'll cover in a later presentation, but I just really want to focus on hardness at the moment. So here we have two fairly typical cutting tool coatings. One of them is a titanium carbonitride coating, and the other one is a titanium aluminium nitride coating. Now these are quite interesting because down at room temperature and even at 250 degrees Celsius, there's a fairly clear ranking in that the titanium carbonitride is significantly harder than the titanium aluminium nitride. So we may just say, well, there we are, the titanium carbonitride is superior to the titanium aluminium nitride as a cutting tool coating. But when we actually increase the temperature, and bear in mind that some of these high-speed cutting operations actually take place at over 500 Celsius, then we see that the ranking switches. And now, in actual fact, the titanium aluminium nitride does a better job of retaining its hardness at elevated temperature. And in fact, in actual cutting tool trials, it's been shown to outperform the titanium carbonitride. Mike mentioned in his presentation that the choice of indenters is important, and that sapphire is a seemingly very nice indenter material to use for elevated temperature measurements, particularly from its chemical inertness perspective. But unfortunately, as he also said, its hardness drops fairly significantly with temperature. And this is an example where we really do have to use the cubic boron nitride indenter. So we're going up to 600 degrees Celsius here, and in actual fact this rather complex coating system, which was made at McMaster University in Canada, has actually retained a hardness of about 22 gigapascals even up at 600 degrees Celsius. So another very high temperature application, this is a 750 degrees C application, is looking at materials for seals for solid oxide fuel cells, and in actual fact this is a glass ceramic material. Now these devices operate at elevated temperature, and they are operating for quite some time, and they have some mechanical load on them. So characterizing their long-term deformation with respect to temperature is important. There are two samples in this study. One of them has been aged at 800 C for 4 hours, and another one aged at 800 C for 100 hours. The objective being to try to stabilize the material against ongoing plastic deformation. So first of all, what we see is, our chart here of reduced modulus versus temperature, is that the aging process at 100 hours has actually reduced the response of the material to changing temperature in terms of the way its reduced modulus changes. If we actually have a look at the creep data, what we have here is a chart that shows us the change in depth in nanometers under the maximum load. So we've loaded up, we've held that maximum load for a period of time, I think it was 180 seconds in this piece of work, and then we've looked at the difference in depth. So that 100-hour aging process has actually given, actually had an effect that means that we get half the amount of creep taking place than we would with the 4-hour aging process. That work was done in conjunction with Georgia Tech. So one more application where time dependency is important. This is a P91 steel material, which is used as a high temperature and high pressure steam pipe material in the power industry. So we've got two sets of data here. One where we've loaded up to 100 millinewtons, and then we've held for 40 seconds at the maximum load. Some creep has taken place, and then we've unloaded. And the other set of data we've loaded up and we've held for 300 seconds, and then we've unloaded. So what's quite important here is that we design our measurements properly, because this ongoing creep of the material can affect our calculated results. So as you can see here, it's fairly well known to this material that the Young's modulus is about 110 GPa at 650 degrees Celsius. So what we find is if we don't allow our creep to develop fully so that the creep rate slows down, the ongoing deformation of the material can affect the unloading slope. So it's just a phenomenon of the material. You'd see this happening at room temperature with a polymer. So we see the result is a higher than we would expect to see modulus. If we allow our creep to fully develop into steady state, so slow rate steady state creep, then our modulus value comes back down very close to exactly what we'd expect to see. So moving away from indentation and moving on to some other techniques which can be undertaken with the nanotest at elevated temperature. The first example I'd like to look at is micropillar compression. So this is a relatively new technique. A lot of people are very interested in this. The beauty of it is that it eliminates a lot of the complex contact mechanics between a Berkovich indenter and the sample surface. So what you can see on the left here is a stress strain chart. And this is some work done at Cambridge University. Essentially, we've got three different groups of temperatures here. We've got room temperature stuff, then this green set is taking place at about 200 C, and then this red, orange, brown sort of color set is taking place at about 400 C. So what we see here at room temperature is predominantly elastic deformation, small amount of plasticity, and then snap. So these are silicon micropillars. And then at higher temperature, 200 degrees Celsius, we see a bit more plasticity, no fracture. So we drive some plastic deformation and we get a bit of recovery. And then we see extreme plasticity. So we've loaded up lots and lots of plasticity. And even though we're reducing the load from this point onwards, the material continues to deform. So what do those micropillars look like? This is what they look like. So at 25 degrees Celsius, the pillars collapsed, as we saw. At 200 degrees Celsius, we see we get still quite a bit of elasticity. The pillar has squashed down and then it's recovered quite significantly, but we get this cracking taking place. So there's a combination of different types of deformation taking place there. And then this is one of the pillars that underwent the very extreme plastic deformation. You can actually see various slip planes which have moved here, and the deformation has taken place by virtue of those planes existing. So Microcantilever bending is another technique which is relatively new to the scene. And in this case, focused ion beam device is used to machine a cantilever or a bend bar, as some people refer to them, into the surface of a material. In this case, the sample is silicon. This image is 60 by 60 microns. This is a fairly wide bend bar. It's about 4 microns wide, and it's about 20 microns, about 30 microns rather long. So we create the image using our nano positioner stage, which is compatible with the high temperature stage. So there we use the indenter to create a 3D image of the surface. Beauty of this is we can then simply click on what point along this cantilever we would like to place the indenter, and then we can carry out a bend test. So we can look at, what we looked at in this case, the response of the material with respect to temperature. So there's a couple of example curves here. Now, just as a point of note, these loading segments took place over several minutes. So particularly in the 700 Celsius case, to allow plasticity to fully develop. So in the case of 110 degrees Celsius, we load up linear elastic deformation and then snap. Okay, so load up, snap. The cantilever's broken off. At 700 degrees Celsius, initially we're fairly elastic, then we go into this kind of mild sort of plasticity, and then very, very extreme plasticity. We actually stop loading when we reach 2 microns. We define that in our experiment details, and then we start to unload. And as we saw, even with the micropillars, as we start to unload, even though we're reducing the load, we still get some ongoing deformation of the cantilever. But in this case, the cantilever has not cracked. So there are many more applications that I'm more than happy to speak to individuals about. And if you'd like to know about those, I'd be very happy to help you. So you can have a look at our website, or you can contact us on info@micromaterials.co.uk. Thank you for your attention.